Hello, everybody. Whoa. I gotta fix this. Let's see. Okay. I was getting feed. I can hear myself, and I really, really don't like it. Oh, I bet if I close that, it'll work better. It's not working better. So, is anyone getting any echo on this? Because I think I'm just gonna... Okay. Well, all right, good. I'm getting echo, so today I'm gonna do this without headphones. I don't really want to figure out what the problem is right now, so okay. Anyway, hopefully you can hear Choo Choo snoring. She is going to join us for this presentation today, or for this stream today. All right, let's get started. Hey, everybody! All right. So today we're gonna do some cool stuff. We're gonna do some hacking on TenderJIT today, and I want to do like. So what I'm gonna do is we're gonna start out and talk about how Callframes work and how method calls work. Well, I guess I'm gonna explain that here in a minute. So let's just get started, I suppose. Where is the keynote? Keynote, come here. Okay. Hi YouTubers. Hello. I can't see the chat now. Yes, this is a professional. I'm a very professional streaming setup here. Okay. So I was thinking about maybe pivoting this channel a little bit. Man, I can't see the chat. I want to see the chat. Where is the chat? There it is. Okay. Come here, chat. Chat. Oh, that's not nice. If I bring up Keynote, I can't see the chat. Well, anyway, let's do this over here, maybe? No. Okay. Maybe Safari, if I view it in Safari. There we go. Okay, cool. I can see the chat now. All right, so anyway, I was thinking about pivoting this channel a little bit to maybe mechanical keyboard ASMR. Might be more fun than, I don't know, programming or something. But seriously, I think next time I might try doing PCB design on this channel. So if there's anything you want to see besides programming, let me know. But I mean, I want to keep the channel like pretty programming centric. I actually really enjoy working on JIT, like TenderJIT, and to be honest, I think I usually find the time to do that during streaming. So I might keep up with that. But next week or not next week, in a couple weeks, I'm definitely going to do PCB design and snoring cats. We're always going to have snoring cats on the channel. So updates. So I was supposed to do streaming, like I had originally said I would do streaming on January 7th. But this is actually my first streaming of the year. I feel like I haven't done video streaming all year. But unfortunately I got COVID-19 and it really sucked. So I didn't like it, and that's why I didn't do streaming a couple weeks ago. So I definitely don't recommend getting it. Like, don't do it. It's not my recommendation. So don't do that. Old business. So I'm trying to do Robert's rules and run this channel like a I don't know, like a like a homeowners association board meeting. So old business. Last year we talked about the top n instruction, which just brought the or took the nth stack value from the top of the stack and then put that or the nth value in the stack and just push that onto the stack. So this is like, so for example, say we have a Ruby stack that looks like this. The top n instruction, all that's going to do is take the nth value, whatever that is, grab that out of the stack, and then push that onto the top of the stack. Oh, and by the way, if any of you have questions while I'm giving this presentation, like just put it into the chat and I'll answer it. Okay, so that's top n. So that was the top n instruction. Now new business. I got the top n instruction implemented, and then I ran TenderJIT against the opt-caret to see what was failing, like where we were exiting the most. And the place where we're exiting the most is on method calls that have star args on them. So like if you do, foo, and then you do like splat, whatever, that's where we were exiting. And so I thought this time what we would do is talk about calling methods, or like how method calls work in Ruby, and then also talk about local variable access, like how do we access local variables, and then how stack frames work. So Yarv is a stack-based virtual machine. I've talked about this many times, and just as a kind of a refresher. So for example, we have some code that's like 5 plus 3 here, and we do put object 5, like we turn this Ruby code gets turned into bytecode, then the virtual machine executes the bytecode, and if we walk through this bytecode, for example, we'll do like put object 5, it pushes 5 onto the stack, then we do say put object 3, pushes 3 onto the stack, and then the add instruction will pop the 2 values off the stack and then push the value 8 onto the stack. So some key things to know about this is the stack is really just one big array. It's just a big array. And we can manipulate that array. We can push values onto that, put values into that array, and then like index into the array. But the important thing is like it's one big array, and we don't have to just push and pop values on it. We can insert values and point at values. Anything you could do with a normal array, we can do that. We can do that with the stack, but it's just one big array. So onto stack frames. Like, let's talk a little bit about how stack frames work. Like, I think we talked about manipulating the stack, but we haven't really talked about stack frames. So I want to talk about that. When we push a stack frame, or when we call a method, we have to push a stack frame onto another array. The stack frame is similar to the value stack, but this is just a different array where we store stack frames. And if you look inside of the Ruby source code, you'll see what's called an execution context, or an EC, and that EC always points at the currently executing stack frame. So let's take an example here. We have what do we have here? We have method A that's calling B, that's calling C, and then we print out the stack. So the way this works internally is we actually push a stack frame on. So we push the stack frame A, and this push happens before we actually enter A, and this is kind of important. So we push that on, and then we enter A. And then we also update the EC to point at A. So the execution context knows it's pointing at A, and we're going to execute A. And then we do the same thing. So let's say we call into B, we push B on as a stack frame, and then we enter B, and then we do the same thing with C. So we're always pushing the stack frame before we actually enter the method. Then when we leave, we actually pop the stack frame. Like, the stack frame gets popped before we leave the function. So right before we leave the function, we pop the stack frame. So we'll pop C, then we'll move that up, pop B, and then we'll leave B, pop A, and then we'll leave A, etc. And all the EC always updates this. Or we always update the execution context with the currently executing stack frame. So important thing to take away from this is stack frames are also really one big array. So the values we have in the stack, that's one array. Stack values or stack frames themselves are another big array. So we have two, like really two big arrays we're dealing with. The stack frames are also called control frames. So if we look at Ruby source code, we'll always see like references to a control frame. That control frame and stack frame, it's the same thing. And the type in Ruby source code is called the RB control frame T. So that's the type that's used to represent a stack frame. And you'll see like a lot of code referencing control frame pointers. So that's CFP. That's always gets shortened in the source code to CFP. So you'll see like the EC points at a CFP. So EC means execution context. CFP means control frame pointer. So you know, like when you see that code, you know you're dealing with stack frames. So let's take a look at how stack frames and the stack work together. So we kind of saw like pushing and popping for stack frames, but like how does that work along with the stack? I wonder how I can say this differently, because we have a stack frame stack, like we have a control frame stack, and we have like a value stack with like two different stacks. So let's look at how they work together. Here is a method. So we've got, let's see, what is this? These are instructions for the two chunks of code in here. So we've got one that pushes 5, and then we have, so like right in the middle are the instructions for main. That's like the 5 plus number, so that method call. And then we have instructions for number. So like we have two sets of instructions that we're dealing with here. So those are the two instruction sequences we're dealing with, and I'm going to take those and combine them together, and we're going to see how these instructions work along with call frames and how the stack gets manipulated. So kind of rearrange the frame here so you can see we have instructions for main kind of there in the middle, and then we have instructions for number. We're going to walk through this execution. We're going to walk through this Ruby code and see how the stack frame or the stack is manipulated along with the call frame. So we're going to see those two things work together. So first off, we always start out with a main stack frame. So when the program starts executing, we're already set up with a main stack frame, and that stack frame points has what's called a stack pointer or an SP, and that points at the value stack. And I've color coded this here. So the main frame is pink, and then its SP is also pink. So the stack pointer that's associated with the main frame, those colors are put together. So we also have a program counter, and the program counter points at whatever instruction we're going to execute next. So here in this case, we're pointing at put object 5. We execute that. It pushes 5 onto the stack and then advances the SP or the stack pointer forward. So the stack pointer is always pointing at the place where we're going to write to next. So we wrote 5 and we push that down. So the next instruction is we're going to push self. So we push self onto the stack. We push SP down. So our stack is currently 5 and self. So the next thing we have to do is we actually have to call the method. We're going to call the method call this method number. Now we're able to look up that number method from self. We know the context from the stack. We look at self and we can say, hey, we look up number based on self. So we'll actually pop that value self off the stack, and then, well, we don't actually pop it. We just rewind the SP1. And then we push the number frame onto the stack. So we haven't actually entered the number method yet. We're just pushing that frame onto the stack. Then we write out 3 magic values, which I'm not going to get into in this talk, but we put 3 magic values into the stack. And then we say, okay, with this new call frame number, we're going to associate what's called an EP with that value, that magic 3 value, which we'll talk about a little bit later. And then an SP for the number frame. So at this point, we haven't actually entered the number function yet. We're about to enter it. We've pushed the number frame onto the stack, and we've set up its stack pointer and its EP. And now main's SP is pointing at this value self. Okay, so now we'll actually enter the function. So we enter the function, the PC for that function points at put object 3, and it pushes 3 onto the stack, and then moves the SP down. So then the next instruction is leave, and this is where we're actually going to return from the number function. And what happens when we leave is, first thing we do is, show it, we pop the value 3 off the stack, so we rewind the SP, and then we pop the number frame. So we haven't actually exited the number function yet, but the number frame gets popped, and then the leave instruction actually pushes that value onto the caller's frame. So whoever called into number, like we pop the number frame, and then whatever the current frame is now after the pop, that's where we push the return value. So the return value gets pushed onto main in this case. And then we don't deal with any of those other values anymore, and we finally return control back to the main function. All right. So then we continue on. We pop 3, pop 5, and do the add instruction. We push 8 onto the stack. All right. So the caller is the one that actually pushes the frames onto the stack, and then the callee is the one that actually pops the frames off the stack. Now the callee pushes the value onto the caller. So frames actually share this stack, and when I said this stack is one big thing, it really is. All the frames share the values on this stack. So just to reiterate, when we're calling a method, we actually pop argc plus 1. So argc is the number of arguments that we've supplied to that function. So in this case, like we called number, but we didn't pass any values to it. So in this case, argc is 0. But we want to rewind 1 because of that self. So we have to keep the stack in line. So we say we pop that off right here. SP is rewound. Self is still there. We don't actually write anything over that value. We just rewind SP a little bit. So argc is the number of arguments. Let's take a look at how arguments are passed. So here's another example. We're going to call number with 3 parameters. We have 1, 2, 3. So the bytecode for this is just put self, put object, 3 put objects, and then a call to number. So we push self onto the stack. We push 1, then we push 2, then we push 3, and then we actually call out to number like this. So if we look at this in the context of actually pushing stack frames, this is what it'll look like. We're just going to revisit the call frame and the stacks. So the PC is going to be at put object 3. So we've just pushed object 3, and now we're going to call number. And when we call number, again, we're going to push a frame before we actually enter number, and then we have to rewind SP by argc plus 1. So argc in this case is 3. We have 3 arguments, and then self. So it's always 3 plus 1, or it's that argc plus 1, and the 1 accounts for the method that we're calling on. So we put magic in, and then we rewind SP all the way back up here, and then we can finally enter the number function. So we'll enter it. Now what's interesting is we can actually address locals as relative offsets to the execution pointer. So in this case, like when we need to figure out like where do we access A, we know that A is actually EP, this EP minus, what is that, 1, 2, 3, 4, 5. So A is EP minus 5. So B, and then B is EP minus 4, and then C is EP minus 3. So these local values are stored on the stack, but we push them onto the stack before we actually entered the function. So if we actually go in and look at the get local instruction implementation, we can see that it's like, that's exactly what's going on here. We say, okay, we're going to get the EP, the execution pointer that's stored on the frame, and we're just going to subtract some index from that. And then that's how we're able to access the values. So now what do we do? Like, that's great. We understand how we can call functions by passing explicit parameters. But how does this work? Like if you have something like this, where you're doing like func and then you splat an array in. And this is the case that I want to deal with today, because this is where we're getting exits in TenderJIT when we call into optcaret. So let's look at the instructions for calling a method like this. We just have 3 instructions here. We do put self and then dupe array, and then we do our actual function call. So if we look at the stack in this case, like look at the values on the stack before we call into the function, we'll see we have self, and then we have an array 1, 2, 3. So that's the stack that we have, but that's not the stack that we want. The stack that we want is something like this. We need to have self and then 1, 2, 3, because the function that we're calling expects 3 parameters. So we have to somehow get the stack we have into the stack that we want. So in order to do this, we actually have a few things going for us. We have information about the caller. So we happen to know, like, okay, we were called with 1 argument, and we also know that the callee wants 3 parameters. And the other thing that we know is that we were called with an arg splat. So we know that we just have 1 argument, like we were given 1 argument, we splatted it out, but the callee wants 3. So all we have to do in this case is we know, okay, we're just going to pop a value off. We'll pop off this array, and then we're going to take the contents of the array and match that up with the parameters of the callee. So we know that the callee wants 3. So we're going to say, like, okay, well, let's just push the 3 values from the array onto the stack. So we'll push 1, 2, and 3 in this case, and then we'll finally enter. All right. So now we're at the actually coding part of this presentation. Let's move this over here and then go to the desktop. I can't see OBS. Oh, hey, there's the chat. Okay, neat. All right. So I'm actually going to do this now. Boy, why is this, like, it's very annoying. The chat does not stay on top for some reason. Yeah, this is a new machine. I don't know what I did. Like, I don't know all the settings. All right. I'm just going to keep Safari up over here so I can see the chat. All right. So first thing we need to do is write a function. Like, actually, I wanted to show something a little bit. Let's go. So I was talking about, like, the EC and the CFP, and I want to actually show that inside of the Ruby source code. Because, like, I don't know, I think it's just a lot easier when you actually see it. So if we look for, like, I guess it's not going to be in here. I don't know. We'll see it eventually. But, like, you'll see references to, like, here's the EC. This is our execution context. And you'll see things like CFP, like this reg CFP. And that's the control frame pointer. That's the current stack that we're dealing with. Actually, we can see it. We can see it all throughout here. Like all this stuff that's dealing with control frame pointer. So, like, for example, here we're doing a get class variable, and for some reason we need to look at the frame for the get class variable. Oh, we probably have to look at the frame for get class variable because it depends on the context that we're in. So we need to know what frame it is that we're in. So, I mean, there's different places throughout here, but I think, like, understanding some of the names is really helpful when you're browsing through Ruby source code. So CFP means the frame. EC is like a global execution context. Actually, let's see. All right, back over here. So let's write our test case. Actually, let's make a test case, not like this. What did we have? We want to do something with splat args, so let's do def number a b. Oh, thank you. Yes, I feel much better. I'm much happier now that I'm COVID free. Yes, indeed. So let's do this. Star 1, 2, 3. And actually, you know what I'm gonna do? I'm gonna have this return an array. C, B, A, like that. So we'll just have it reverse it, like that. Actually, let's comment this out for now. and then look at, we'll dump the instructions for this. So you can see, let's make this a little bit wider. So right here, this is our definition for number. So that's the number method. And all it does is a put nil and a leave. So now you can see like why an empty method returns nil. It's because when the leave instruction gets called, we have a nil on the stack. So here is the actual call. We're gonna do put self and then a dupe array and an op send without block, and we get argc is 1, and then we're doing a splat on that. So we know what we have here. We have 1 argument and 1 splat, and that's being sent to self. All right, so let's write a test case for this. Op send without block test. We'll put it here. And what I want to do, like, I really wish that I didn't have echo in my headphones. I'll have to figure that out. All right. So we're going to call this, and we're just going to reverse the array. That way we can, like, I just wanted to do something. And the reason I want to return essentially a reversed array is so that we can verify that the parameters are being passed into the method in the right order. So let's do def test splat. Okay, and I'm just gonna do like, just gonna copy this. Let's see. We don't care about has reader. We're just gonna call number list equals 1, 2, 3. We'll call number, and then we'll star list, do that, and then we're gonna compile number. Oh no, we can't do this. This isn't gonna work. So we have to actually, like, we have to compile a function that calls this with a splat. So we can't just call the function, or we can't just compile the function. We gotta compile a function that uses splat. So this isn't gonna work. Let's do def call number this. We'll do number star 1, 2, 3. Okay, so we're not going to do that. We're just going to do call number, and then call number. We'll compile that and then call it again. Now we expect to have what? We're going to compile 2 methods, actually. We're going to compile call number, and we're also going to compile number. So we expect 2 to be compiled. We expect 2 to be executed, and we also expect 0 exits from the JIT. All right, so let's run it. Run it. And wrong Ruby. Run it. Let's see what we see here. Okay. Expected 0, actual 1, and that is on line 423. Oh. Okay. So we successfully compiled 2 methods, but and we successfully executed 2 methods, but we exited from the JIT, and that is not what we want. We want to make sure that we stay inside of the JIT the entire time. So let's go in and fix this, and this is in lib TenderJIT IC compiler. So this is in our instruction sequence compiler, and I believe, like, right now we're going to exit here saying this method is too complicated. Let's check. Let's see. Is there a specific reason I'm using? Nate is asking if there's a specific reason I'm using trunk Ruby. Not particularly. Mainly just to keep up with changes on trunk. That's about it. Like, TenderJIT right now only supports trunk Ruby and 3.0, like the latest 3.0. Let's see. Let's go to opt back over here. Luan is asking, why wouldn't compiling the number method work? Well, we can compile the number method, but the issue is that what we really want to test is we want to test the call site that contains the splat. So we can call number, like, if we just compiled number and then called it from here, we wouldn't be compiling the call site that calls number. So we need to be testing like this case where the splat comes in. That's why we're compiling this method instead. Okay, so if I print out, what is it, like pjit dot, what is it? Boy, I haven't worked on this in a while. There should be like an exits, exit stats. Who has exits? Ah, here we go. pjit.exit stats, and this is going to give us a hash, but I think it's going to be gross. Oh, probably want to print it before we fail. Yeah, see, there's like a bunch of stuff here. We don't really know why, so let's do like find all. Okay, v is greater than 0. Okay, let's look at that. If we run this, okay, yeah, so this is our exit reason. We're exiting because the method is too complicated. That's just a name I gave it. There's like no, it's just complicated, too hard. This method is too hard. All right, so let's fix it. So in here, I had this thing, like I added this thing that's like supported call. And what this does is it looks at the call site and it says like, hey, it reads the attributes about the call site and it says like, can I compile this? Like, do I know how to compile this? And if we look at this method, it basically is doing a bit mask against the information in the call site. So right here, like we don't handle splat or keyword splat or tail calls or calls to super or all these different ones. We handle block args, like all the ones that I've commented out here, it handles. But like if we looked at the dump of these instructions, you can see here we have an arg splat at the call site. So that's what we're trying to implement now. It says we don't support it now, but we're going to try supporting it. So let's do that and say, yes, this is a supported call. And actually I want to do another thing and be like, I'm kind of interested if this is like splat. Let's make a splat thing that's like, okay. VM call args splat. Okay. So let's go back here. So I'm just making a predicate method to test, like, I'm not 100% sure if that's the right flag. I think it is. I mean, it has the same name, but I just want to like check. So let's go into IC compiler and be like, hey, is this a, let's do PCI dot splat. And then I'm just gonna exit. Cause like this will, if we don't exit, it'll generate some machine code that might be like crashy. I don't really want to deal with crashy right now. So let's take a look. Oh no, let's run the test. Let's see. So yes, it's a splat. So this is we're compiling a splat call site. So we'll say, I guess, yes, it's supported. Let's print out the argsy, p-argsy. Make sure we're actually getting what we expected, because we saw it, like as we saw on the slides, argsy should be 0 or should be 1, because we're calling with 1 parameter. Yes, it is 1. Cool. Let's see. The next thing I want to do, so TenderJIT is able to, when it pauses to compile a method, it takes a look at self on stack. We've pushed self onto the stack, and it's able to take a look at self and do stuff based on what self is. So like right here, we're saying, hey, actually, let me put this at the top of the screen. Stack, give me the top n value of the stack, and argc should be 1. So 0, like the 0th element is going to be that array, and then the first element is going to be self. So that should be the receiver, but this is just the address of the receiver. So down here we can say, hey, I want to get the address of the receiver, and I want you to convert that into a Ruby object. So if we actually print out, like if we do prb receive and then exit here, this should actually be, let's go back to the test case. So the receiver in this case should actually be the test case instance. So if we run this, we should see the test case instance printed out. And yes, it is the test case instance. So it looks like we're pretty good here. What do we need to do? So, okay. Let's get that array. Like we want to know, we need to get the array and see what's inside of it. Let's try to get access to the array. We should be able to do like, let's see, top n stack 1. Does that seem truthy? No, 0. It could be 0. Yeah, because it's the top of the stack, right? Yes. And that will give us the address of the array. So if I do like pfiddle.dl unwrap that. Okay, so if we do this, we should be able to get access to the actual array contents. Let's run this. And nope. Let's see. Why not? Top n2i. Oh, I'm sorry, because that needs to be a DL unwrap. Come on, pair program. That's right, we're pairing with Aaron today. Pairing with Aaron. My YouTube pair programmers are supposed to catch these errors. Come on. All right, so we were able to get access to our array. We can see that yes, this is the array. Here it is. We were able to pull it out of the stack, and we can do stuff like, let's do rb splat rb array equals this, and we can figure out like how many elements it is and how many we need to push onto the stack. So I think in this case, what we want to do, we're gonna try to do, we're gonna write something super hacky. As opposed to all of the other non-hacky code that's in here. So we gotta pop 1 off the stack because that's the array, and then we're gonna take the array contents and push the array contents onto the stack. So we'll do this. We'll say, let's see, temp stack dot pop. Oh, and I've frozen the stack. We're gonna have to reassign it. So let's do like this. Let's do if what was it? No. Supported. Was that a thing? Yeah, ci.supported call if ci.splat. So we only want to handle splat cases. And say like, okay, if this is a splat, I'm gonna pop 1 off the stack, and then I'm gonna write it just kind of as pseudocode here, and then we'll actually like make it go. We want to do like rb array dot size times, so that number of times we want to push onto the stack. Temp stack dot push. We're gonna push an unknown value because we don't know. Like, keep putting those semicolons. Writing too much C code. Jeez. So we're going to push all the values that are inside of the array onto the stack. So we pop 1 off. And then that ought to do it. I mean, this makes sense to me. But we're going to have to do this temp stack equals temp stack dot dupe because it's frozen. Nate says that I've been writing too much JavaScript. I think he might be right. Actually, I think maybe I should pivot this YouTube channel to be like JIT for Web 3, something like that. Get all those Web 3 subscribers. Okay. So we're gonna push it onto the stack a few times. Okay. So we can't just push onto the stack. We actually have to get the values out of the array and push those values onto the stack. So we're gonna do, boy, what is it? We gotta access the internals of this this array. Let's do that. Let's do rt.temp var do temp. So we're going to create a temporary register. So basically the plan is we're going to allocate a register. We're going to put the array into that register. And we want to do that because we need to access the elements of the array and also push onto the stack. So we need a temporary variable to hold on to the array while we push the array contents onto the stack. So we'll say temp here, and we're going to do temp.write, temp stack.pop. That ought to do it. Let's do this. Let's do rt.break. Actually, let's set a breakpoint here. So I'm going to try running this under LLDB, and then hopefully we'll get a breakpoint here. Let's do rt.nop. So we should see a nop instruction after the breakpoint, so we know that we're in the right place. And then maybe we can do like nop like that. So hopefully we'll do a write to a register here, and this register will contain the array that we popped off the stack. So let's do this. Please work. Oh my goodness. Yes, it worked. Wow. Okay, lucky. So we have our nop there, and then I don't know if this is big enough. I'll make this a little bit bigger. There we go. So we have our nop here, and then this is where like our temporary register is R9, and we're putting this value from the stack into R9. So let's step over these instructions one at a time. So we'll step over the move, the copy, and then now we should have like let's pull this in. Oh, that's not gonna work. Okay, I'll pull those in. Oh, what? Why? I don't really need to give this my whole like. Okay. Why is this? Is that not actually the directory? Let's see. ls. Oh. Ruby get ruby mist ldb what? Oh, cruby. Great. Yes. Okay. Run it. Run. Hit our breakpoint. And then we're going to do script. I already forgot the command. Yes, I know that's wrong. Okay, great. So after we execute that mov, R9 should contain the array. So if we do rp$r9, yep, there is our Ruby array right there with 1, 2, and 3 stored inside of it. So we did it. Nice. Okay. Well, we did it. It's stored into a temporary register. Great. So the next thing we need to do is we got to push, like we got to read from the array, read the elements. So we're able to access the array in the machine code, but we need to get those elements and push them onto the stack. So I think I have some helper functions for that. Let's see. Actually, I definitely do. Yeah. So we can treat this pointer as an array. So we can say like, hey, I want this as an R array. So let's do array equals this thing, and that. And essentially what this does is gives us kind of a nice DSL for accessing the members of the struct. So it does all of the arithmetic for us for figuring out where those members are. So we'll say like, okay, we're gonna break here. We got a pointer to an array here. It's of type R array. And we're just gonna do this. We're gonna say, whoa, I deleted too much there. RB array dot size dot times do, and then we're gonna say, I'm gonna push onto the stack, and this is some location to write to. So we'll say like, let's see, rt.write location array.as.array I. Okay. So here we'll say in push the values of the array on the stack. Okay. So I think that'll work. Let's do another breakpoint here and like walk through it and make sure it actually did what we wanted. General question, do you think JIT in Ruby would be the default for all use cases, and would we run it on all of our Ruby codes with it? So I think that would probably be true for YJIT, mainly because the startup time is so low that you probably wouldn't notice even in regular scripts. Like the only time I think you wouldn't use it is if you had a very, very short script that only like you just ran the script and then exited. That's the only time I think you might not use it. But really the warm-up time on YJIT is so small that even then it's probably fine. Let's see. All right. Oh, I should have just done run. Okay. Run. Oh, probably need a comma there. What is up with my YouTube pair programmers? Come on, people. It's supposed to be a comma there. Okay, so here's our first mov, which is popping that array off the stack. So we can see like right here, we're getting the array off the stack into R9, and then here we're saying, hey, read out of R9, put that into R10, then put R10 into the stack. So our stack is stored in R15. Nate is asking, what memory trade-offs are you expecting with YJIT? My Ruby scripts use 50 megabytes of RAM. After YJIT, it uses more. Nate, it'll use more megabytes of RAM. I don't know how many. You can tune it if you want to. And then Matthew is asking, is that times loop implying a static compile time array length? And yes, it totally is. That is a good question and good catch, which will, after I get this thing working, we'll address it. But well, I guess I only have maybe 12 minutes left. But basically what I want to do, or what I'm thinking about doing, is saying like, okay, we're going to embed this particular length. So when we get when a call site comes in, we compile a call site, we'll look at the array length and say, okay, it's 3 or whatever it is. And then at runtime, we're going to check it again. And if it's not 3 or not the value we compiled for, we'll recompile that. I don't know if that's a good strategy or not, because if people are calling tons of stuff, like calling some function with a bunch of different array lengths, like maybe it's not a great idea, but yeah, that's what I was thinking of doing. Okay, so let's see. Si rp string r or $r9. Okay, so that's our array. So if we do this one, we should have the first element of the array in R10. So let's do rp $r10. Yep, there it is, 1. And then the next instruction is pushing that onto the stack. So I think R10 is going in there, and this R10 should be the second element. Let's just do that, rp $r10. Yeah, it's 2. Okay, so it looks like this is. Oh, Nate is asking, my first instinct was that significantly increased memory usage would be a reason to not always be on by default. Yeah, that's a good point. Yeah, that's probably a good point. We don't want to increasing memory by default probably isn't a good idea. Yeah. So maybe don't turn it on by default. I don't know. All right. So it looks like this loop is working correctly. So we're able to do this. Like this works. It seems like we're pushing onto the stack. Actually, let's try reading off of the stack. We'll do RP what do we want to do? R value star. No, let's not do that. Let's do this. So the stack is stored in 15, but we're storing it's an offset, or R15 never changes, so we keep pushing on to the end of it. So we got to look at what R15 sub, what's 10 in hex? I can't even remember. Let's just try 10. No, it's probably not right. Oh, okay, maybe it is right. Ah, yeah, that should be right. Yes, because it's R15 plus OX10. Yes, of course. Okay, so if we run this and this and this, if we look at 18, that should be 3. Oh, okay, I don't know. Whatever. Seems to be working. But we have kind of a problem here. Like, so argc is still 1. Like, if we print out argc here, p argc, exit. Let's exit. We're not going to do breakpoint anymore. If we print out argc and then run this, so argc is still 1, and that bookkeeping is broken, so we got to fix that. So let's say, oh, hi Mike, good to see you. So let's say argc is the length of the array. What is that? RB array dot size -1. So we'll increase it. We'll increase it by that. Okay. So argc, like the argc bookkeeping should be correct now. Let's look. So let's try running just to test. Well, yeah, let's try running it. See what happens. Okay. So we're getting an index error on IC compiler 1081. Let's go look at that. That is here. So we're looking at, it's peeking into the temp stack. Okay. So the compilation request stores a reference to the temporary stack. So at the moment that we have a deferred compilation, TenderJIT will take a copy of the temporary stack and save it there and freeze it. So we know, like, anytime we need to recompile, we know exactly what the state of the stack was at that point. And what we're doing here is, like, this particular call, like compilation call, is just asking that compilation request, hey, give me back the temp stack at the time that this happened. But since we're splatting out an array before we actually call into the function, we're mutating the temp stack, or we're changing the temp stack. So this temp stack is the wrong one. And if we look at the call trace here, like, we were in compile send, that's where we were doing modifications, and then we're calling into compile call iseek. So I think really what we need to do here is, instead of asking the request for a temporary stack, let's like pass it in. Because if we look, like, compile call iseek is here, it's right here on this line, and then up here in the same, I admit this is a very long method, but in the same method we're actually manipulating the temp stack here. So what's happening is the temp stack on the request is only of length 1, whereas we need it to be length, what, 3 or 4, something like that. So let's pass it in. pass it in there. And this needs the temp stack here. And then down here, we don't look at the temp stack. Okay. Let's try running. It worked. It worked. Okay. Wow. All right. So it did what we wanted. We compiled 2 methods, we executed 2 methods, and there were 0 exits in the JIT. Works great. Let's do one more test, and I think I'm gonna stop now. So Matthew brought up the point of like, okay, like this is a compile time value. So we know, like when we compiled this call site, we saw that it was 3, but what if it's a different value? Like it could be something else. That is a huge issue, and I want to try, like, let's try breaking it. So we need to somehow figure out a way to, let's just pass the array in. Let's do this. Let's do that. We don't have to hard code the array in here. All right, do that, and then let's do like, that ought to do it. And then let's make sure this still works with 3. Oh, we don't want to splat it here. There we go. Okay, so it still works with 3. So let's try heating it. Nate, yes, I like your solution very much. Size 3, too big. We only support 3. So let's do, like, what should we do? Let's try heating the cache with 3. So this will heat it right here. Let's make a copy of this. Oops. Yeah. So let's make a copy of those. Test splat like breaks. So we'll heat it with 3, like this. So this heats it. And now let's call it with 4. Actually, this will probably work. Let's see what this actually prints out. I think this is gonna work. No, it's not gonna work. It's not going to work. It won't work. It's gonna break. Let's see, test splat breaks. Okay. Yeah, nice. Segv. Okay, so the reason we'll talk about the reason this broke, and then I think I'll stop the stream today. So the reason this broke is we have an issue here. Not only do we have this issue with the size of the array, like it matters what the size is, so the size has to match up between compilation time and runtime, but we also have an issue with access to the array. So I believe this array is going to be, like the first one that we saw is 3 elements, so it's only an embedded array. If we grow up to 4 elements, we have to do a malloc, and then that malloc is going to have a buffer, and then we'll have to go read the values out of that buffer rather than read them from inside of the array itself. So we actually have 2 different problems here. We have an access problem, which is a size problem, or we have a size problem. We also have an access problem. So where to find those values at runtime. All right, I think I'm gonna stop here. I'll finish this up probably, and then send a pull request with to TenderJIT with these changes. Well, some of these changes, but I'm gonna make it like work better in more cases. And let's see, next week, where is the keynote? Not next week, in a couple weeks. I think I'm gonna do this again on February 4th. And I guess we'll probably do PCB design that week. I don't know if it's gonna take an hour though, but anyway, thank you all for coming. I hope you have a good Friday and a good weekend, and it was good to see you all. Bye. Next week, yes. Next week, size arrays 4.